We're going to finish off our chats about probability distributions with the geometric and binomial distributions, which are specific models for determining the probability of finding a certain percentage of objects within a larger group, or how long you have to wait until you find a particular type of person or thing. So we're going to start with the geometric distribution question, and we're going to start by talking about people who are not in grade 9. So if I'm doing a geometric question, the thing I'm asking myself is, how long am I going to have to look until I find someone who is not in grade 9? So if I have a 75% chance that someone is not in grade 9, that should make sense, because a typical high school has kids in grades 9, 10, 11, and 12. That's 4 different grades, and only one of them is grade 9, so it's about 25%. If I wondered what the probability of the first person I asked not being in grade 9, well, that's easy. That's just 75%. So first person, 75%. But if I couldn't find someone not in grade 9 until the second person I asked, you kind of have to put this in context. If I'm waiting to the second person to find someone not in grade 9, that means the first person must have been in grade 9. So for this scenario, I walked up to a random bunch of people in the cafeteria and I grabbed one and said, "Are you not in grade 9? And they said, "Oh God, yes, I am in grade 9, sorry." I said, "Okay, fine." And then I went to the next person, and that person was not in grade 9. So what had to have happened here is that I found someone who was in grade 9, 25% chance of that happening, and then found someone who was not on my second try. The next scenario, so I either find this non-grade 9, the first person I ask, or the second person I ask, or maybe it's the third person I ask. But in order for this scenario to have unfolded, I had to speak to one person who was a grade 9, a second person who was a grade 9, and only on the third did I find someone who was not. So that would be 0.25 for the first grade 9, then another for the second grade 9, and then another who is not in grade 9. Just to make sure this pattern is completely clear, if I don't find a non-grade 9 until the fourth person, then the first person I asked was a grade 9, 0.25. The second person I asked was a grade 9, 0.25. So was the third, 0.25. And only the fourth person was not in grade 9. So as I'm going up through this list, the further down I go, the more grade 9s I had to find first before identifying the first person who was not a grade 9. So I'm going to take this and I'm going to put it into a chart. So x, that'll be the variable, that's going to be the ranking of the person I find who's not a grade 9. Is it the first person? Is it the second? First. Is it the second? The third? The fourth? The fifth? The sixth? The seventh? The eighth? The ninth? Etc. So if I were to put these numbers here into this chart, the probability of finding that grade 9 or the not grade 9 on the first go is 0.75. The probability of finding a not grade 9 on the second try means I had to have found 1 grade 9 before I found the type of person I was hunting for. If I find that person on the third try, it means I must have stumbled across 2 grade 9s. Notice I've used squared here. This times this is the same as 0.25 squared. It makes it a little shorter to write, especially when I get into these longer lines. 0.75. If I find this person on the fourth time, I must have had to find 3 grade 9s first. Or maybe I found 4 grade 9s first. Or maybe I found 5 grade 9s first. You see how this goes. Now, I'm going to keep drawing this list because there's a point I need to make to you, and I'm going to need many rows to do it. Generally, we stop making these charts after the 5th or 6th row. These probabilities are going to shrink down to almost nothing as we get deeper. And if you think about that, it's not hard to find somebody who's not in grade 9. It's not hard to stumble into a grade 9 first and then find someone who's not in grade 9. But it would be strange if you walked blindfolded into the cafeteria and found a grade 9, then 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 a grade 9, before finding someone who was not. There's just not enough of them for that to be plausible. But that is what this row is here. Right? Stumbling into 8 grade 9s before you find someone who is not. And when I actually calculate these decimals, we should see the sort of diminishing return as we get down there. So I'm just going to erase this so that we have some space. There's a little gap here, and I left that gap tactically. I can fill that in. 0.25. How many grade 9s did I find here? Well, I didn't find any. And if you check your exponent laws from grade 11, then any number to the exponent 0 just is 1. So if you're multiplying by 1, it doesn't matter. Check that with your calculator. So I'm going to go through and I'm going to actually do these calculations. And I'm going to flip into fast forward mode at some point so that we can just get through it more quickly. Basically, the first one, 0.25 to the exponent 0 is 1. Multiplied by 0.75 gives me 0.75. This next row, 0.25 multiplied by 0.75. Let's try that again. 0.25 times 0.75 75 is 0.1875. And look what's happened to that probability. There is quite a drop from this outcome to that outcome. For this one, 0.25 squared is 0.0625 multiplied by 0.75 is 0.046875. And I'm going to cut it off at 4 decimal points. 0.0469 if I round. This row here, 0.25 cubed times 0.25 times 0.25 is 0.15625 multiplied by 0.75. I'm having some calculator rage right now. 0.25 times 0.25 times 0.25. 0.15625 multiplied by 0.75 is 0.1171875. If I round it to 4 decimal places, I'm at 0.0117. Now, if you notice, something that will speed this up for you, the only difference between this number and this number is that I multiply by 0.25 an extra time. So to get to the next row, you're really just taking this number and multiplying it by 0.25. Then you take this number and multiply it by 0.25. And then you take this number and multiply it by 0.25, etc., 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 down the chart. So I'm just going to do that so we can get to the end. Times 0.25 is 0.0029 times 0.25, 0.0007 times 0.25 is 0.00018. I'm going to round that to 2 times 0.25 is 0.00005. And one more time, just because I've drawn the chart already, 0.00001. All right. So as you can see as I go down here, the probability of wandering into the cafeteria and blindly choosing person after person after person and getting 8 grade 9s in a row before you found someone who was not a grade 9 is getting pretty hard to do, right? That's 0.001%. So that's bordering on statistically impossible. So you can see that sort of dropping as we go. The last thing I need to ask is what is the expectation? Right, so how long would I have to wait? How many people do I expect to ask? Before I find someone who is not in grade 9. Well, we've done expectation values when we were doing the games of chance. And so the way you did that is you took the probability of an event happening and multiplying it by the value at which happens. Now in the games we were doing it this times the prize, because the prize is really all you cared about. In this particular question, it's this number, right? Did it happen on the first person? Did it happen on the second person? So there's a probability of 0.029 that it's the 5th person you ask is the first one you find who's not in grade 9. So I'm going to make my expectation column by taking how many people I had to ask multiplied by the probability that it was that many people. So 1 times 0.75 is 0.75. 2 times 1.1875 is 2 times 0.1875. 0.375. And then 3 times 0.0469. 3 times 0.0469 is 0.1407. 4 times 0.0117. 0.0468. 5 times 0.0029. 0.0029. 0.145. 6 times 0.0007. 0.0042. 7 times 0.0002, 0.0014, and 8 times this would be 8 times 0.1, 4 zeros and a 5, it's 0.0004, and 9 times this one, 9 times 0.1, 2, 3, 4 zeros and a 1 is 0.00009, which I'm going to round to 0.001 because I'm only keeping 4 decimal points. Okay, so when we were doing expectation values for games, you had to take the amount that you budgeted here plus the amount that you budgeted here plus the amount you budgeted here, and you had to add them all up. So I'm going to do the same thing. I'm going to take 0.75 and I'm going to add 0.375 and I'm going to add 0.1407 and then I'm going to add 0.0468 and then I'm going to add 0.0145. Then I'm going to add 0.0042 and 0.0014 and 0.0001. I'm going to get 1.3327. Alright. Now you might have noticed that this chart isn't done. I mean, it is technically possible that you could find 9 grade 9s and then the person you're after, or 10 grade 9s, or 11, or 12. Technically this list goes forever. Now, if you're in the cafeteria at your particular high school, eventually you run out of grade 9s, and that is a limitation of the model. But if you were doing something that wasn't quite so finite, like you were digging through water molecules and like Huron, hunting for a heavy water molecule, there are a lot of those, and you would likely lose interest before you ran out of water molecules to check. So this chart technically never ends, which means that this answer here is only an approximation, because I have to add up all these values for an infinitely long chart. Now I have better things to do with my time, and so do you. Because you notice that once I got to here, and this is only the 9th row, the amount I'm adding to this is way down here. It's all the way down in the 10,000th place on this digit. So my answer is going to be pretty close to 1.33. Now that's a funny number, 1.33. That's awfully close to 1.333333 repeated, which happens to be 4/3. Now if you take a look up here into our starting information, 75% of my people, that's 3/4, are not in grade 9. So it looks like the expectation value is this fraction, but flipped. So if I were to write that for you as an equation then, or as a relationship, I'm going to erase this and I'm going to do some summarizing for you, and then we'll come back to that. So if I summarize that for you, a geometric distribution is useful, right? This model applies anytime you are hunting for a specific object or type of person, and that you're going to keep asking people until you find one of those. So this is, perhaps you've heard the colloquialism, your keys are always in the last place you look. Well, obviously, because once you find them, you stop looking. So your keys are always in the last place you look. But the point of that little colloquialism is that you kept hunting until you found your keys. So what's the probability that you find your keys in the first place you look? What's the probability that you find them in the second place you look? Because you're going to keep looking in places until you get your keys. And if that's the activity that you're doing, you are following a geometric distribution. So if you were to reach blindly into your cookie jar and keep pulling out cookies until you found a chocolate chip one, that's a geometric distribution. Because as soon as you get your delicious chocolate chip one, you stop and you leave, leaving all the disgusting raisin nonsense all over the counter. So if that's what you're doing, a geometric distribution is for the behavior of hunting until you find what you're looking for. And if that's the case, the expectation value for this distribution is 1 over the probability of finding the thing that you're after. So if you were trying to hunt for, let's say, left-handed people, you're going to walk through the room until you find a left-hander. The probability of a person being left-handed is about 15%. So the expectation then, expectation for a left-hander would be 1 over 15%, 0.15. So if I do that, 1 divided by 0.05, 1 divided by 0.15 is 6.667. So I would expect at a 15% probability of a person being left-handed that I wouldn't find one until the 6th person I asked. If it took me longer than that, something curious is going on, because I should have found a left-handed person by now. If it takes me less than that, something curious is going on, because I shouldn't have found a left-hander so quickly. That's sort of how this works. If you were going through a room of random people, and you ask them, are you left-handed? Yes or no. Are you left-handed? Yes or no. And you keep going until you find someone who's left-handed. That's hunting until you find one. And you would expect to ask 1 over 15%, which is 6.667 people, before you found one. So we're going to take this, I'm going to get this out of the way, and I'm going to ask a few questions about probabilities of finding people. So this is how these questions work. I've generated this table, and then I need to acknowledge that this table does in fact go on to infinity. It never stops because it's a geometric distribution. Once I've developed this chart, 5 or 6 rows of it, I'm going to be asked a question like this. What is the probability of finding a non-grade 9 for the first time? And this is the phrase here that triggers geometric distribution, right? This phrasing implies that I keep asking people until I find a non-grade 9 for the first time. What's the probability of finding a non-grade 9 for the first time on the third person? Well, third person, there it is. The answer to that is 0.0469. I just had to pluck the row out of the table. The next type of question you might be asked is, what is the probability of finding a non-grade 9 for the first time in less than three people? So notice this was on the third person, and this is in less than 3 people. So less than 3 people would be the first person you ask or the second person you ask. So if I look at that in the table, it could happen this way or it could happen this way. So when you say that word or, it means you have to add those probabilities together. So the probability of finding someone in less than 3 would be 0.75% that you find them on the first try, or 0.1875 that you find them in the second try. And if I add those together, 0.75 times 0.1875, it's not that, 0.75 times, no, plus 0.1875 is 0.9375. So if you walk into the cafeteria and you start asking people at random to find someone who is not in grade 9, you have a 93.75% chance of finding someone who is not a grade 9 in less than 3 people. Perhaps you can intuit what the next type of question was. What is the probability of finding a non-grade 9 for the first time in more than 4? So what is the probability that it takes you more than 4 tries in order to find someone who is not in grade 9? Now that's a tricky one for this table, because more than 4 would be this row, and the 6th, and the 7th, and the 8th, and the 9th, which I've erased. But it also includes the 10th, 11th, 12th, 13th, etc., all the way to infinity. That's no good, because I don't want to make an infinitely long table. We've said this before. You have better things to do with your day than write this table forever. So we're going to be a little tactical about it. If I'm asking a question about more than 4 people, that means it's every row except this one, this one, this one, and this one. So if I add all these rows up, I should get 100%. But I don't want this row, because finding them on the 4th person is not more than 4 people. I don't want this row. I'm going to take it out, because finding it on my 3rd person is not more than 4. I'm going to take this one out, and I'm going to have to take this one out. Because finding someone on the first try is not more than 4 people either. So, forgive me while I swear at this calculator for a little longer. 100% minus 0.0117 minus 0.0469 minus 0.1875 minus 0.75 leaves me with 0.0039. So there's a 0.39% chance of it taking more than 4 people. Now, that's a neat little answer, because there are an infinite number of rows here. So if you started typing in these numbers, right, this row plus this row plus this row plus this row, you would never finish, because there's an infinite number of them. There is no end to that list, so you would be typing into your calculator forever. But if you did, if you took forever to add all those numbers together, that's what they'd add to. So this idea that an infinitely long list of numbers has a finite sum that's a very peculiar outcome, right? You shouldn't be able to add an infinite number of things and get an exact value at the end, especially not one that small or that tightly defined. But that idea is sort of fundamental to calculus, and it's fundamental to probability and statistics in that if you have a set big enough, sometimes that set will actually whittle its way down into a nice tightly defined number, which is sort of neat to think about. All right, so we've done expectation for a geometric distribution, and we've done questions like this: on the third person, less than 3 people, more than 4 people. The other one you have to watch is the phrase at least. So if I say at least 2, that means 2 is okay, and 3, and 4, and 5. More than 2 is 2 doesn't count. So in this case, more than 4 people, I threw away everything that was 4 or less. If I had said at least 4 people, then I would have had to throw away 3, 2, and 1.